Okay, then the way that I'm imagining it is that you have a pendulum and I don't know how the pendulum apparatus is supposed to be when you actually measure, but I'm just going to say that it's completely still. And then you see, does it move slightly to the left or move slightly to the right because it's attracted to
Right.
the person who goes to the left or to the right?
Right.
Okay, you're saying that actually, if you were to look at that pendulum, it would be constantly jittery because just even without anyone going through the doors.
Right.
Oh, okay. So what I was about to say is could this not be solved with more precision, but then you would have to do a series of measurements.
Yeah. So, I mean, the most famous gravity measurement is probably the Cavendish experiment, where they sit there with this, beam with two weights on the end, and it's held up by a string, and it kind of rotates like this, and you use that to measure, say, the gravitational field of the Earth or of two balls of a kilogram mass, for example. And if you ever have seen that experiment, or you've tried to do it in, say, an undergraduate physics lab, you'll see that the torsion pendulum kind of moves about quite a lot and is jiggling much in the way that we just described. And the reason it's jiggling is mostly because air molecules are hitting it, and the system is very noisy, and there's heat, and we don't have very good control of gusts of air, which push and pull the pendulum. But imagine that we got rid of all those gusts of air and had everything in a perfect vacuum and didn't have any stray electromagnetic fields or gravitational fields around, but we cleaned up everything. Would there still be some fundamental noise? And this theory predicts that there will be. And it's this noise which somehow allows interference patterns, because the gravitational field, because it's random and noisy, it doesn't allow us to really determine which slit the particle went through.
Now, the quantum field theorist would say there is noise anyhow because there's some fluctuations. So is there a way of you distinguishing the noise from the fluctuations versus, I don't know what type of noise this is called, but this post-quantum noise?
Yeah, that's a very good question. And there is disagreement. So, I've had disagreement with some of my colleagues about this. But we've calculated how much noise there has to be, and there has to be a lot more noise if gravity is fundamentally classical, there needs to be a lot more noise in the gravitational field in comparison to the quantum case. And it's true that in the quantum case, you also need some noise there, because you can imagine the same experiment, the double slit experiment that I just gave. You can imagine the same argument being made about the electromagnetic field. How is it that if the particle goes through the left slit or the right slit, I can measure the electromagnetic field, and what is it about the electromagnetic field which doesn't allow me to determine which slit the particle went through?
So what is it about the electromagnetic field?
Right. Well, it's as you say, it's the fact that there is, we can't measure the electromagnetic field to arbitrary accuracy. I can't measure because the electromagnetic field has a quantum nature. Then I can't measure with exact precision, the electromagnetic field and say its conjugate degrees of freedom. So because we can't measure the electromagnetic field to arbitrary accuracy, we're not able to determine which slit the particle went through. Or another way of saying it is this: in quantum mechanics, you can have two different states which cannot be distinguished. In other words, the electromagnetic field will be in a different state depending on whether the particle went through the left slit or the right slit. But even though the state of electromagnetic field is different, I still can't tell it apart. It has, some overlap. Both states, there's overlap between the two states, and those two states are not orthogonal, we would say. In other words, they can't be distinguished perfectly. And it's because those two different states of the electromagnetic field are not distinguishable. It's that which allows you to still have an interference pattern. Now, sometimes you don't, right? Sometimes the particle will go through the left slit and it will emit a photon because it happened to hit the wall in a certain way. And if I were to measure that photon, I would be able to determine which slit the particle went through. So there is some decoherence. The interference pattern does get disturbed a little bit by the electromagnetic field, but not by very much.
This theory of yours doesn't have predictions. So one prediction I see is that it's a null prediction, namely that there is no graviton.
Right.
Does it have other predictions? And am I even correct by saying that there is no graviton?
Right. There's gravitational waves, but there is no quantized particle which is responsible for carrying the gravitational force. So one of the big predictions is this noise in the gravitational field. So we predict that you should go and do the Cavendish experiment, and you will have to see a large amount of noise in the gravitational field. Now, the problem is that there is already a large amount of noise in the gravitational field. If you ask the people at NIST who are responsible for keeping the 1 kilogram mass and telling us how keeping that to and doing these precise measurements of, say, a 1 kilogram mass, they will tell you that it's actually a very difficult experiment to perform, and that their measurements do have quite a large variance and inaccuracy. So the experiment we're proposing is higher precision tests of those measurements of, say, a 1 kilogram mass in order to put a bound on how much noise there is in the system. I mean, what's exciting, even whether or not you believe in, I feel like this question of whether gravity is fundamentally quantum or classical is a real one. And I think what's exciting is that this actually allows us, through these precision Cavendish measurements, to actually determine whether gravity has a quantum or classical nature.
Would the noise, if you were to, with precision, measure the gravitational field, would that noise still be there even in other approaches to harmonizing gravity with quantum mechanics like string theory, where you sum over metrics? So like there is some uncertainty as to what the gravitational field is in string theory. So would they say that should also produce noise, or is this noise distinguishable from the noise that you're talking about?
So there will be some noise, and it has in some ways a similar form, but the amount of it is just much less in a quantum theory. And the reason is that in a classical theory, you can perform, in some sense, two different experiments. You can do a precision test of gravity and see if there's noise in the gravitational field. And the other thing you can do is you can do an interference experiment. So I can take a gold atom, for example, a very heavy atom, and see if I get an interference pattern. And if you get an interference pattern, you can keep pushing how coherent you can make a gold atom. So I might imagine a gold atom that can be in can follow two different paths and be in a superposition of these two different paths. And if I can keep the gold atom in superposition for a very long time, then it would mean that I need a large amount of noise in the gravitational field in order to keep that coherence. So there's a trade-off in some sense between how long I can keep a gold atom in superposition and how much noise there needs to be in the gravitational field in order for the gold atom to keep being in a coherent superposition. And there's a trade-off between those two things. And so I can perform both those experiments, and if I can, and the longer I'm able to extend the coherence time of gold atom, the more noise I know there must be in the gravitational field if the gravitational field is classical. So between those two experiments, you could either rule, you could potentially say rule out the classical theory of gravity. Whereas in the quantum case, there's no such trade-off. You don't need to have, there's a related trade-off, but it's not quite the same. And so it turns out that for a quantum system, if the gravitational field is quantized, then there doesn't need to be nearly as much noise in it.
Understood. If one wants to read up more about this, which I'm sure many, many people do, what would be, forgive the pun, the canonical paper of yours to read?
So there's just, there's a recent Quanta article which you mentioned, which is, probably reasonably accessible to a popular audience.
I'll put the link to that in the description, as well as to the Quanta video of yours.
Great, thanks. And then, the first article was called A Post-Quantum Theory of Classical Gravity. And that is quite a detailed article, but at least the first 2 or 3 pages, tries to explain, this Feynman argument and why it doesn't rule out a classical theory of gravity. And then it also discusses, one of the big reasons that people disregarded the fact that we could have a classical theory of gravity was that they essentially assumed that having a classical theory of gravity was equivalent to something called the semi-classical Einstein's equation, where you just take the expectation value of the stress energy tensor and then stick that into Einstein's equation. And that's been known for a long time to be a pathological equation. If we take it as fundamental, it leads to all kinds of problems. And so people somehow associated semi-classical gravity with attempts to keep the gravitational field classical.
What's so pathological about it?
So it doesn't satisfy this principle of linearity, which I said is so important, and which I think any theory ought to be linear. And when you have a theory which depends on expectation values, then it allows you to do all kinds of things like superluminally signal faster than light, or in some sense violate the uncertainty principle, because if you can measure an average value, then that's a pretty weird thing, right? Like in a single go. Like here's a way of explaining it.
Okay.
Imagine that I flip a coin, and with some probability, I put a planet on the right, and with some if I get heads, I put the planet on the right, and if I get tails, I put the planet on the left. And now imagine that I have a theory where I am attracted to the expectation value of those two state of affairs. So on average, the planet is neither on the left or the right; it's in the middle. And so what happens in a theory where you take expectation values is that if I drop a test particle towards and watch the test particle free fall towards the planets, they will fall straight down the middle between the two places where I would have put the planets. So, here's the planet if I get heads, here's the planet if I get tails. If I take the expectation value is somehow down the middle, and that's where the particle falls. And that's, of course, not what we expect to happen. So a theory where you use expectation values rather than, say, something else is going to lead you into a world of pain, essentially, because of that.